Some of you are not. So I thought what I would do, as I did the last time, is give you a little summary of what we've talked about in the past, which will remind you a little bit about what we've done if you were here, and maybe provide a little base if you have not been here before. So one of the first things that I said about this series is one of the most fundamental assumptions that I make in looking at these issues is that there is one truth, and there is an objective truth that is intelligible, that we can learn about, and for whatever it is something we can learn about and make a decision about. And it would include things that are seen and unseen. It may include God, it may not include God. It may include one universe, it may include many universes, but whatever it is, I do believe there's an objective reality that is intelligible for us. And I think we have an opportunity to determine that for ourselves, to determine what the truth is, and then to live our lives in accordance with it. Science is an important way to understand a lot of the reality in which we find ourselves. But science also has some important limitations where it cannot provide answers. It's simply outside the scope of what science can do. And when that's the case, there is an answer, there is an explanation, but it's not something science can provide, and something else will have to be looked to provide that explanation. We also looked at knowledge, how we gather knowledge, how we process knowledge. And we gain knowledge about the external world through our senses. We also have knowledge that we generate through our internal and subjective world about our deep sense of morality, our relationships and love, and also revelation about God if you are a religious person. And reason is something that we use to understand both of these, to make sense of the information that we derive from these sources. All human beings are differently calibrated, and we filter information through our own set of physical characteristics, but all through the set of experiences that we have during our lives. Because science is primarily the interpretation of data, it is subject to these same limitations. Human beings are doing the interpreting. They're subject to the same filtration and cognitive biases that we all have. Finally, everything we know is really a form of belief. Last week we talked about physics, and I congratulate those of you who were here for sitting through 45 minutes of physics. And what we figured out is science is really very good at figuring out how things evolve, how things develop over time. But it's really not very good either at the why question or how things begin, how things are created. Science has made a number of observations about the world that it accepts as true, but it can't explain. And I gave a few examples of this. One is there are four forces that underlie everything that happens in the universe. Those forces have specific values. Those values are required for the universe to exist the way it does, and they appear to be immutable. Science has determined that those are true. It believes those are true and uses it in its process, but it can't explain why they're true, why they're where they are. Science has also determined that the universe is intelligible through mathematics. That's the language that science uses to make it intelligible. And then there are things like the absolute nature of the speed of light, which it has determined, but can't tell you why it has the speed it does or why it's absolute. We also talked about two of the major theories that govern the way the universe works, general relativity and quantum mechanics. Both have been experimentally verified many times over. General relativity deals with the large structures and large and fast things. Quantum mechanics deals with the very small. There's a probabilistic nature in quantum mechanics, but we have not figured out how those two things work together. They seem to be in conflict, but we know both of them are true. And so one of the things we found through physics is that reality is stranger and more mysterious than anything we would have imagined. And it really does press the limits of human intelligence and imagination. So this week we're going to talk about the universe. And we're going to begin with the beginning of the universe and the Big Bang Theory, not the TV show, but the scientific theory. Before 1927, the universe was thought to be static. The stars didn't move very much, and really eternal in the form that we saw it. This was very consistent with what Aristotle believed back in the 4th century. But in 1927, Edwin Hubble demonstrated that light emitted from distant galaxies was redshifted. I'm not going to go into what that is exactly, but the light was redshifted, and the redshift also appeared to increase the more distant the galaxy was from us. And so what that means is the galaxies that are further away are moving faster than galaxies that are close to us. So George Lemaitre, also in 1927, who was also a physicist, took this data and sort of ran the expansion of the universe backward and came up with a theory that the universe had expanded from a single atom, which exploded and created the universe. This theory got its name from another astrophysicist named Fred Hoyle, who called it derisively the Big Bang, but it stuck. So these two theories of the static universe and the Big Bang and the expanding universe were really in competition until 1965. And one of the things that was predicted by the Big Bang theory is that there would be a remaining cosmic microwave background radiation, very low level of radiation throughout the universe. And when that was discovered in 1965, the Big Bang became the accepted theory. So let's talk about what the Big Bang is. What the Big Bang theory suggests is that the universe really began 13.8 billion years ago. And it began with something called a singularity. And a singularity is a point that is infinitely hot and infinitely dense. There is no space and there is no time when the singularity existed. And the first thing that is believed to have happened is called inflation. And what happens in inflation is space itself expands at an enormously rapid rate, way faster than the speed of light, and created a universe of space. The next thing that happened is that space began to continue to expand, but at a lower rate, and it began to cool from its initial temperature of 10 billion degrees Fahrenheit. As space expanded and it began to cool, the four forces split into separate forces, particles began to form, and that began the universe. Now, everything I just told you is believed to have happened in the first second after the Big Bang. A lot happened very quickly. Then, over time, as the universe expanded and cooled, matter coalesced and stars and galaxies began to form. And that happened about 400 million years after the Big Bang. So that's really the theory in a nutshell. And how do we know this? The way that we know this is that we have made, number one, we have learned a great deal about forces and general relativity, because this deals with the very large and the very fast. General relativity is really the key to understanding the Big Bang. And this theory could not have been developed without it. But the other thing is we're making observations about the universe. We're looking at how is the universe structured today? How does it operate? And so if we run this tape backwards and figure out what does this tell us about how it was formed over time? And remember that when you're looking at far distant stars and galaxies, you're looking back into the past. There are a number of criticisms about the Big Bang Theory. One is that it does not address the creation of the universe. It really deals with the evolution, beginning with a singularity and running it forward. It doesn't deal with the singularity and how that was created or what may have come before it. Also, there are a number of observations, some very important ones, about about how the universe is right now that are not consistent with the Big Bang Theory. And I'm going to name a few of them, but there are a number of other ones, but I'll just give you, so you get sort of a sense of what this is. The cosmic microwave background radiation is extremely uniform throughout the universe. The Big Bang Theory says it should not be. There's a problem called homogeneity, which is that the universe at a very large level is highly homogeneous, but just slightly not homogeneous, not completely homogeneous, so that stars and galaxies can form. And we really don't understand why that is the case. And then there are the magnetic monopoles. I know this has been a big question for you in your life, but magnetic monopoles are really what they sound like, where you have a particle where only one pole is magnetic. The Big Bang Theory predicts that these would be a dominant form of matter throughout the universe, and we've never seen one. So these are what I would refer to as known unknowns. We know we have these observations, and we can't explain it with the Big Bang Theory. There are some competing theories. There are two string theorists, Paul Steinhardt and Neil Turok, who have developed their own theory that there are 3D membranes that collide in four-dimensional space, and the universe generates itself and regenerates itself over very long periods of time. This looks a lot like the Big Bang Theory. It's very different. I mean, it sounds crazy, but one of the reasons that people are looking at things like this is this theory explains a number of things the Big Bang Theory cannot. There remains some dispute about it, as in many parts of science. But one of my fundamental questions about the Big Bang Theory is whether or not is it really science. If you look at the situation that you have in developing the Big Bang Theory, we really can't experiment and can't directly observe what happened up to 400 million years ago. At 400 million years, stars and galaxies began to form, and we can go back in time by looking in the very distant universe and see those. But beyond that, we can't see it. If you look at what we have done with quantum mechanics and general relativity, we discovered how those work by being able to make direct observations about how the world really was. And we simply can't do that with the Big Bang Theory. And you know, the scientists, particularly with quantum mechanics, when they observed how the world of the very small really worked, they were sort of dragged kicking and screaming into this because no one had developed this, no one had theorized about quantum mechanics. It was really a process of discovery. But one of the things I want to make clear is so this is really, in my view, and I know a lot of scientists would disagree with me, but it's really mathematical philosophy or scientific speculation. And I want to be clear that I don't believe that this work should not be done. I take it extremely seriously. I think it's important work, and I think we should do it. But I think we need to be realistic about the limitations that we have in trying to roll that clock back. And I'll give you an example, just a small example, but if you look at the weather system on planet Earth, we spent a lot of time studying that. We have direct access to it. We do that work a lot. And right now, we're at a point where we can predict the weather about 5 days out pretty accurately. Everything after that's pretty much an educated guess. So if we're having trouble doing this, rolling this thing forward or rolling it back with weather that we can see, touch, and feel, and it's a relatively complicated system on Earth, how much more complicated is the universe? And trying to roll that tape backwards and forwards is extremely difficult, I think. All right, so that's the Big Bang Theory. So let's talk about the structure of the universe. And I want to start, and we're going to do a little show and tell today, but I want to start at the Earth in our solar system and sort of work our way out. one of the most important scientific efforts we've ever done, I think, were really the Voyager 1 and 2 space probes, which were launched in 1977. The goal of those space probes was to take advantage of an unusual alignment of the four of the outer planets, Jupiter, Saturn, Uranus, and Neptune, and be able to send these space probes by them and also use them to increase their speed so they could get their work done more quickly. This is a rendering of one of the space probes. They were about 1,500 pounds. There was Voyager 1 and Voyager 2. And just to give you a sense of, remember this was 1977. Computing was not very well advanced at that point. And the computers on this had about the same computing power as this key fob that I have in my pocket. And yet they did what they accomplished, which I think is really quite remarkable. Voyager 1 went by Jupiter and Saturn and then went beyond to the edge of the solar system and beyond. Voyager 2 went to those planets as well as Uranus and Neptune. And so I'm going to go through a little bit of what they did and tell you about their journey. The first stop was Jupiter, which was in July 1979, about 2 years after they left. And Jupiter is 318 times the mass of Earth. It has more mass than all of the other planets combined. It's an enormous body. It is a gas giant, about 75% hydrogen and 25% helium. And its most notable feature is the active atmosphere that it has. And this is a picture of its atmosphere, which is really quite remarkable. The red spot, which is a storm, that's about the size of the Earth, has been observed on Jupiter since 1830.
Before we had a better estimate of how many galaxies and therefore what the mass of the universe is. How does the discovery of 10 times more galaxies affect our concept of what the mass is? It doesn't maybe affect us very much locally, but on a universal scale, how does it affect us?
Briefly, I think that the dark energy outweighs the visible energy. The dark matter outweighs the visible matter by such a degree that I don't think that's going to matter. But let me get through this, and then we'll have some more questions later. The last thing that I wanted to just touch on here, and I'm going to talk next week about the origin of life on planet Earth and about evolution and the evolution of man. But I thought in this context I would touch a little bit on whether or not there is extraterrestrial life. And if you simply look at the numbers of stars and planets that must be out there, just statistically you have to believe if it's here, it's probably got to be somewhere else. But as I'll note next week, habitable planets are probably more rare than you might think, and creation of life from non-life may also be much more difficult to initiate. But even given those factors, if there is intelligent life somewhere else in the universe, what is the likelihood of our being able to identify it or communicate with it? Well, I think the first thing to note is we have no evidence of life in the solar system at this point other than on planet Earth, and certainly no intelligent life. So we're looking out somewhere beyond our own solar system. And if you look at what I would call man's footprint on planet Earth, if you are if you're on a planet somewhere else a million light years away, it's going to be very hard to detect it. I know we have electric lights and they look really nice from a satellite going around the Earth, but if you're a million light years away from us, it would be enormously difficult to even see that. And then you get to travel is of course out of the question. I mean, the distances are just so great, it's entirely out of the question. But then you get to the element that I think is interesting, which is the element of time within history. In order for us to communicate with some other intelligent being, you have to be very precisely aligned in time and space to be able to communicate with each other. If you look at us on planet Earth, we've only had that capability for about 100 years. Well, 100 years in cosmological time is absolutely nothing. And how long do you think the human race is going to live? One of the things that we have found through evolution is the most striking element of evolution is that most species end in extinction. 99% plus have ended in extinction. And humans are also the first species on Earth to have the capacity for self-destruction. So how long will we last, and what is the likelihood that we will be able to align ourselves almost perfectly with another intelligent being to know that they're there? So that's the universe, the short course on the universe. And these are really the conclusions and takeaways from today's session. First, we have no ability to scientifically determine what happened at or before the Big Bang. We can't see back to 13.8 billion years. We have no ability to see past our own universe. We can't even see all of that. Based on current theories concerning dark energy and dark matter, we don't know what makes up 95% of the universe. And the basic structure of the universe means that we are, for all practical purposes, alone. So that's the universe. Next week we're going to talk about the origin of life and evolution and the formation of man. I invite you to stay for a little wine and snacks, which are always great. And if you have any questions, I'll be glad to try to answer them.
I've heard that the galaxy comes defined by a black hole. They all have black holes. I've never heard that there are multiple in the same galaxy. That Andromeda need to show a specific example of this around the black hole.
That would be the expectation. The thinking now is almost every galaxy probably has a large black hole or multiple black holes. Yes, ma'am.
Take me back to elementary school and define a galaxy.
Excuse me?
Take me back to elementary school and define a galaxy.
A galaxy is a formation of stars that is held together by the gravitational pull on each other, basically.
You mentioned the word light years, which is frequently used in the study of astronomy. But I guess most people don't understand how long a light year is. My understanding is that light travels at 186,310 miles per second.
That's correct.
Each second. So if you say how many seconds for a light in a year, and you multiply the distance times that, that's a huge, huge distance.
Yes, it is. And when you're dealing with billions of light years, you're talking about something very, very far away indeed.
Well, I've never heard that expressed in terms of miles. How many miles do you know?
it's you can calculate it, it's a big one. Yes, ma'am.
I know nothing about telescopes. How do we see all that you described that I can do? The Hubble telescope can
Yes.
see that far?
The Hubble telescope is a very sophisticated instrument. It doesn't have the interference that you get from the atmosphere, so it's really looking out sort of in clear space. And as I mentioned, when they did this deep space experiment and found out there were 10 times as many galaxies, they will leave it focused on one area or one object to allow the light to come and build over time. And so you're really gathering light over time is how you do it.
Gotcha.
Yes, ma'am.
The Voyager.
Yes.
Which is still off the radar.
It's pretty much off the radar. I mean, they know where it is, but we're going to lose track of it in 7 or 8 years.
That's so weird. Where is it?
It's in interstellar space.
I did hear on this trip that there's going to be a new Hubble.
Yes, the James Webb, 2021, which is supposedly even more powerful.
What's propelling?
Well, I mean, once, this is Newton's law, right? So once you have an object in motion, it will tend to stay in motion unless some force acts on it or slow it down. So there's not a lot of resistance in space. And so as it's going 38,000 miles an hour, unless it hits something or something propels it forward, it'll keep going 38,000 miles an hour.
I think it's understood that the universe is expanding.
Yes.
Expanding, but I never have known what it's expanding from what? From everything expanding from everything else? Is that?
And I mean, one of the key concepts here is that it is space itself that is expanding. The galaxies are not moving through space. Space itself is expanding and taking the galaxies with it.
All this stuff. How would you measure that?
You have to ask Edwin Hubble. I'm sorry.
There's a mass involved,
Yes,
which implies there's got to be a particle.
that's correct.
And those are invisible. We can't fix those particles.
Yes, but I mean, the theory is, I mean, we have the ability to detect certain kinds of particles, baryonic particles, and they think this is a non-baryonic particle that also has mass, which is what neutrinos supposedly are massless particles, and that's why they're not a candidate, but we really don't know what it is. Yes, ma'am.
One of Einstein's theories was that sound will never ever go away. It just goes finer and finer and finer, like the Doppler effect, kind of like when a train goes by and you
Right.
hear it, but it's still making sound. Do you think that with as much as we have learned, that later we will be able to detect that?
Detect what? Sound?
Sound, for instance, the Voyager, that we can't, it's getting fainter and fainter and fainter. Do you think
Oh,
that-
if they improve the land-based communication systems, perhaps so, but getting down to a trillionth of a watt, that's a pretty small signal. Yes, sir.
The universe is expanding. Does that mean that Mars and Jupiter's distance with one another is greater now than it was yesterday?
Probably not, but because they are held by the gravity of the sun in a certain orbit. So as far as I'm aware, that doesn't directly impact them. Anybody else?
You, this multi-universes, have you got into that at all with the dark spots and the bumping into other universes, the bubble effect?
I mentioned it briefly last time, talking about string theory, which is really where that comes from. I have not really addressed it here. One of the problems with string theory is the same problem that you have with the Big Bang theory. Most of string theory, there's absolutely no way to test, there's no way to observe, there's no way to experiment. And so, I'm not denigrating the effort that's being made. I think it's important and I think it's interesting, but there's no way to test it experimentally, and that's really the power of discovery in science is really where its power comes from. And, as demonstrated with general relativity and quantum mechanics, we never would have figured that out if we didn't see what was actually happening.
I was just thinking about with the bumping of the universes with the cold spots, which could be a computer glitch too.
Yeah, it could be the Matrix.
It could be. Yeah, absolutely.
Anyone else? Yes, now.
You said earlier that we're on a direct collision course with Andromeda,
Yes.
and in 4 billion years,
That's- yes. Give or take.
we will collide. But you also said that it's not likely that any of the stars would.
Yeah, I mean,
hit each other.
it just gives you a sense, of how large the space is. Andromeda's believed to have about 1 trillion stars. But it is mostly empty space.
Right.
And so if these two galaxies collide, the theory is that none of the stars will actually hit each other because there's so much space between them.
So will we pass directly through?
Yeah, I mean, what's anticipated is they would collide, and then as the gravitational effects take effect over the next 3 billion years, they would keep going back and forth like this until they become one giant galaxy.
Wow.
Yes, sir.
Effort has been made to determine where singularities originated, I mean, where in the universe.
And this gets to the cosmological principles. There's no way we can identify what the center of the universe is, and that's why the cosmological principle is so interesting. I think is that the universe looks the same no matter where you are, right? So there's no edge to it. There's no center to it. We have no idea where the Big Bang started. And this is one of the things science just accepts, is that there was a singularity, and I'm going to tell you what happened after that case. Anybody else?
I was reading the other day, you might have to remember where from the sun, all the different planets in the order they are. And I remember many very elegant men are justly satisfied using nickel paper clips.
There you go.
And that's beautiful.
Except Pluto. No more paper clips. Pluto's not a planet anymore, yes?
Pluto.
No more Venus on planet.
It's a dwarf.
They say.
Depends on who you ask.
The sun will be dead by 4 billion years, and it'll be burned out, so we won't even know about it.
Probably, yes, yeah. I think we may not know about it. All right, well, thank you all very much. Next week is the formation of life, evolution, et cetera, et cetera. So hopefully. Found in this, Voyager found is there are also rings around Jupiter, not nearly as pronounced as Saturn, but they're rings nonetheless. And then one of the most interesting things was on one of its moons, Io has volcanic activity, which nobody realized. And what we have found since then is we believe that Io is the most volcanically active body in the solar system. And so you can see here that that's a volcano with the lava and all the rest of it. The next place they went was Saturn. This is obviously its most notable feature, the rings. This is something I think everyone's pretty familiar with. It is a gas giant like Jupiter, but not nearly as large. The next stop was Uranus, which was in January of 1986. So 9 years after launch, they finally got to Uranus. This is Uranus. It's got a dense atmosphere, so you don't get a lot of definition of the surface. They are both ice giants. They are both much larger than the Earth, but much smaller than Jupiter and Saturn. And Uranus, you can't see them here, but it has rings very much like Jupiter does. The next planet was Neptune, which they reached in August of 1989. And you can see a big spot here. That spot is not a storm. It does have an atmosphere that's not a storm. That's actually a hole in the atmosphere. We don't really know why it has a hole in the atmosphere, but that's what has been observed. But one of the most interesting aspects of their flyby Neptune was Triton. Triton is a moon of Neptune, and these jets here are actually geysers. They are nitrogen, liquid nitrogen geysers. Now, the interesting thing about this to me is that the surface temperature on Triton is 391 degrees below zero. It's only about 35 degrees Celsius above absolute zero. Absolute zero is the theoretical limit of cold. It is the point at which particles do not move and do not generate heat. And so it's enormously cold, and so this is only on one part of the planet, but we really don't know how this happens or why it happens, but it's very interesting, I think, that it does. The next one, I know you think there's a problem here, but this photograph is called the pale blue dot. And you can see this if you go online, and those of you in the front row may be able to see it, but there's a little dot there. And Carl Sagan was very much involved in the Voyager mission, and he was very good at trying to engage people. And so one of the things he lobbied for was to have Voyager 1 turn around before it left the solar system and take a picture of the solar system with the Earth in it. And so that's what this is. It's really a very famous photograph. The other thing that Sagan did is he did the golden record. I don't know if you remember that, but there is a golden record that they put that was intended to represent a lot of stuff about man. They had a picture of a naked man and a naked woman, which generated some interest back then. But one of the other things they did is they had music from all around the world. And they only had one rock and roll song, which was Johnny Be Good by Chuck Berry. And so I just love the idea of Chuck Berry in interstellar space. Voyager 1 is the first man-made object to leave the solar system. It left the solar system on August 25th, 2012, when it passed what's referred to as a heliopause. That was 35 years after it was launched. It is traveling at about 38,000 miles an hour. That means that it could circumnavigate planet Earth 1.5 times in an hour. It's the fastest thing we've ever produced. And so it's now in interstellar space. It is headed toward a star about 17 light years away, which is really very close to us. I know you'll recognize it. It's AC 79388. But Voyager 1 will reach it, and I'd be interested to see if you know how long, 500 years, maybe 1,000 years. Voyager 1 will reach it in 40,000 years. And that's one of the closest stars to planet Earth. It is right now about 13 billion miles away from us. It takes about 16 hours for a communication at the speed of light to reach us. And we are still able to be in touch with it because of the improvements in ground-based communications. But when their signal reaches us, it's only about 1/1,000,000th of a watt. And in about 7 or 8 years, we won't be able to communicate with it at all. It'll be on its own. So as we continue to move out, our solar system is in the Milky Way, and this is a rendering of the Milky Way. We can't take a picture of it since we're in it. But the Milky Way is a spiral galaxy. It is about 100,000 light years across, which is really quite a large distance. At the center, now just to give you a sense of the size of that, if our solar system were a quarter, the Milky Way would be the United States. At the center, we believe that there is a supermassive black hole. As you may know, a black hole is a super dense object which results from the explosion and collapse of a star. That black hole is supposed to have the same mass as about 4 million of our suns. And we believe, and the black hole is, the gravity is so high that not even light can escape it, which is why it's called black. They can absorb other stars, they can absorb other black holes, and we know that there are probably about 60 black holes in the center of our galaxy. There may be as many as 10,000. We believe that there are about 100 billion to 400 billion stars in the Milky Way, in our galaxy, and obviously you can't count that high. So what they do is they try to estimate the mass of the galaxy and then divide that by what they believe is probably the average size of a star to come up with that number. We are part of a small galaxy cluster called the Local Group. It has mainly dwarf galaxies, which are smaller galaxies than ours. Each of those only has about 1 billion stars in it. And then we are part of a larger structure called the Virgo supercluster, which contains about 100 galaxies, including the galaxy Andromeda, this is a photograph of the Andromeda Galaxy. This is one of the closest large spiral galaxies to us. It's 2.5 million light years away. I don't want to scare you, but we're on a collision path with Andromeda. And it's moving at about 670,000 miles an hour toward us, and we will collide with it in about 4 billion years. One of the things that I find most interesting about that collision is that when that collision occurs, it is very unlikely that any stars will actually run into each other because both the galaxies are mostly empty space. So as we move out away from our local group of galaxies here and look more at the large-scale structure of the universe, what we have seen in our area where you have stars that are parts of galaxies and galaxies that are parts of clusters goes on throughout the whole universe. And there is a concept called a cosmological principle, which is something that was first suggested by Isaac Newton. And it basically states that on sufficiently large cosmic scales, the universe looks the same to all observers in all directions. So if you think about that, now we can't test that because we can't go anywhere else in the universe but where we are. But if you think about that, think about how enormous the universe must be for that to be true. However, there are some challenges to that. In August 2007, a new supervoid was confirmed, which is nearly 1 billion light years across. And what that means is there is a void in the universe in which there are no stars or galaxies, and it's 1 billion light years across, which is really quite large. One of the other things to think about when you think about the universe is that if you'll remember what I said a minute ago is that light and the stars and galaxies began to form about 400 million years after the Big Bang. So about 13.4 billion years ago is all we can see. We can't go past that. And because that's as far back in time as we can go, that's also as far as the largest distance we can see. So we're really living in sort of a sphere of the visible universe, which is 13.4 billion light years across. And we really can't see beyond that. We believe that the universe is much larger than that, but we can't see it. We have no access to it. Within that visible universe, the former thinking was there were about 200 billion galaxies. But in October of 2016, they took the Hubble telescope and they focused it on a region of deep space and allowed it to stay there where they could get the light from the most distant galaxies. And when they counted the galaxies, there were about 10 times as many as they thought there were previously. So now we think there are probably 2 trillion galaxies in the universe, in the visible universe that we can see, each of those with hundreds of billions of stars, probably more stars than there are grains of sand on the Earth. So the universe itself is unimaginably vast. What is its future? We know from Hubble's law that the galaxies are moving away from us, and we know that the ones that are further away from us are moving faster than the ones closer to us. But in 1998, using the Hubble telescope, what was figured out is the pace of the movement away from us is actually accelerating. And so the pace of the expansion of the universe is actually accelerating. And what this means is, because what we were looking at previously is the universe is expanding, but is the universe going to expand to a point where it then slows down and goes back to the Big Bang, or is it going to expand forever? Now that we have learned that it's expanding, I think the expectation is it's going to continue, that it's accelerating. I think the expectation is it's going to accelerate forever. If this is true, then over time, the universe will expand to such a degree that we won't be able to see any stars or galaxies. The sky will be completely black. And in fact, all those stars will eventually burn out. not a very happy future, but we won't be around to see it. So how is this happening? And what is it causing the universe not only to expand, but to accelerate in its expansion? And the current theory is something called dark energy. And it's a term you've probably heard, but the concept is there is energy that is diffused in space that is causing this expansion. The most recent theories are believing that energy is actually a property of space. So as space expands, energy expands in an ever-increasing in an ever-increasing way. And so this acceleration will maybe increase over time. The problem is that we have not been able to detect dark energy. We don't really understand it and really don't know what it is. But if the theory is correct, dark energy makes up 68% of all there is in the universe. And if you'll recall, matter and energy are two sides of the same coin. One can transfer into the other. But so if there is dark energy, as they believe, 68% of all there is dark energy. The problems with this are that we have not been able to detect it. Also, our measurements of the far distant universe may not be accurate. So we may not, our measurements that indicate that the universe is accelerating may not be correct. And finally, there may be something going on that's much more fundamental to our understanding of the universe. And there may not be dark energy at all. There may be a force or some other explanation for why this is occurring that has nothing to do with dark energy. Also, you've probably heard about something called dark matter. In the mid-20th century, we began to realize that as we studied various galaxies, they were rotating and behaving in a way that could not be explained by the visible matter that we saw there. And in fact, when they ran the calculations, what they determined is it had to have 4 or 5 times as much matter in the universe than we could see for it to actually behave that way. And so they came up with the concept of dark matter. But again, it's dark because we can't detect it. We don't know what it is. And though we have tried, and they're doing calculations to determine how much dark matter it is and how it's distributed and all the rest of that, but unless we can figure out what it is, it's all just a theory. And one of the questions I think that is interesting about dark matter is we know a lot about the visible universe and the level of complexity and variety that exists in the visible universe. You've seen the pictures from the Hubble Space Telescope. I mean, it's really quite remarkable. Is dark matter, which is 4 times as much dark matter as visible matter, if it does exist, does it have that same level of variety? Or is it just, one type of thing that fills up space? And we don't really know the answer to that. But look at where this leaves us. So now the current theory is that dark energy makes up 68% of all there is. And if you run the numbers, dark matter is 27% of all there is. And that means that what we can see, those 2 trillion galaxies that we believe are out there, is only 5% of all there is in the universe.
One quick question. The calculation of how many galaxies there are expanded by, what was it, a billion or a trillion?
With 10 times what they thought before.
Okay, 10 times what they thought before. So if that's the case, to what degree does that, and the concept of dark matter, dark energy, well, maybe dark matter came about in the 50s or 60s, something like that. Before we knew how many